Part 6 from Chapter 8 is focused on one thing and one thing only. That is the Diels-Alder reaction, which has to do with dienes. Okay? It's another famous reaction because you can use it to make carbon-carbon bonds. And if you recall from Chapter 7, I told that that's not trivial to do in organic chemistry. Okay? So this is another thing to have in the toolbox to make carbon-carbon bonds, specifically to make cyclic compounds. Right? And the 1950 Nobel Prize came from the Diels-Alder reaction. But before we can talk about the reaction, we need some vocabulary to get us there. Okay? As I mentioned, this reaction deals with dienes, and those dienes like to react with a dienophile. Okay? A dienophile is something that actively reacts with a diene. Right? You can kind of get it right from the name, right? Diene and phile, to love. The Diels-Alder reaction is a paracyclic reaction, and it is a cycloaddition reaction, two new terms. Okay, so paracyclic reactions means that it's a cyclic shift of electrons. So electrons are moving around kind of in a circle. And a cycloaddition reaction, right? Cycloaddition. Two reactants come together to form a cyclic product. So addition, two things added together, cyclo, right? It's a cyclic product. So dienophile paracyclic reaction, cycloaddition reaction. Okay. You can see now how this is a cycloaddition. Okay. It forms a cyclic product from these two reactants. We take a diene and a dienophile and put them together to form a ring, a six-membered ring in this case for the Diels-Alder reaction. So let's see what that mechanism looks like to understand why this is a paracyclic reaction. Okay. Well, I take my diene, which is on the left-hand side, and my dienophile together. When they approach one another in the proper configuration, you see the electrons shift around in a circle. A pi bond comes down, a pi bond moves over, acting as a nucleophile here, attacking an electrophile, another pi bond acting as a nucleophile and attacking an electrophile over here. And overall, right, we're moving in a ring. Easier to see there in the transition state. Cyclic shift of reactions, paracyclic reaction. Okay. This Diels-Alder reaction is a 4+2 cycloaddition because it's 4 carbons and 2 carbons coming together. Tells you you must have 6 carbons in the cyclic ring in your final reaction. Okay. Another piece of vocabulary from Chapter 6, right? This is also a concerted reaction. Everything's happening at once. And we're getting 4 electrons that are moving around from the diene, 2 from the dienophile. So that'll be significant. Make sure you're able to understand that mechanism. Okay? Forming 2 new sigma bonds, right here and here, and a new double bond. Right? So we go from previously having 3 double bonds to just 1 in the product, and it's in a new location. And because the other 2 pi bonds, those electrons went to forming the sigma bonds. Okay. Looking at another reaction here, a little more in depth. Right? What's happening? Pi bond shifts over. Pi bond comes over to form a sigma bond. Keep in mind, this is probably the biggest area of confusion with the Diels-Alder. We show electrons attacking atoms, but what's the net result here? The formation of a new sigma bond. That's what's happening here from this arrow. And the same thing's happening up top here to form that sigma bond. Okay. It is a 1,4 addition reaction. And if you see a ring, like thinking about retrosynthesis, right? You see a ring with a single pi bond in it, chances are it could have come from a Diels-Alder reaction. So let's see how that relates to substituents, okay? Because the simplest Diels-Alder reaction, jumping back a slide here, right, just has butadiene there and then a simple dienophile. But that substituent can alter the reaction, as we've seen. Okay. If I have an electron withdrawing group on my dienophile, that increases its reactivity. Okay? Because if I put an electron withdrawing group there, if we think about the resonance contributors, that gives it a larger partial positive right here, and therefore makes it a better electrophile, again, jumping back a slide, for the attack right there from this pi bond. See the delta positive on the resonance hybrid. So if you see an electron withdrawing group, like a carbonyl, the C double bond O, or a nitrile, that makes it more reactive, which is advantageous because it's easier to run. You can run the reaction at lower temperatures, for example. So here's another example of a Diels-Alder reaction. You can do a Diels-Alder with any combination of a diene and a dienephile, okay? But in this case, right, we've got a really nice dienephile because of the electron withdrawing groups. Easy to run that reaction with butadiene. We can also have an alkyne be a dienephile. It doesn't just have to be an alkene. That gives you an extra pi bond in the alkyne, meaning there's an extra pi bond in the final product. Okay, so you have a 6-membered ring with 2 double bonds across from one another. That tells you the Diels-Alder reaction that came from an alkyne. So why is this reaction so common? Let's think about the relationship to the molecular orbital diagrams. Okay? And this is, you'll see why we introduced the terms HOMO and LUMO in the earlier videos. Okay. In order for the Diels-Alder reaction to happen, the orbitals must all overlap, all in phase. Okay? It's called conservation of orbital symmetry. It means everybody has to overlap with one another in phase. Okay? So if I look at the diene in the dienephile, I'm showing one way here, flip the other way, okay, depending on the approach. Right? We need the orbitals from the HOMO, the highest occupied molecular orbital of the diene, to overlap with the orbitals of the LUMO, the lowest unoccupied molecular orbital in the dienephile, for the electron transfer to occur. Right? See the orbital overlap there. So then the question becomes, what if they're not symmetric? Then how do I draw the Diels-Alder reaction? Okay? Because as you see on the bottom, that gives me 2 possible ways to arrange the reactants, which results in 2 different products. Yeah, those are 2 different constitutional isomers from one another. So if you have that case, I didn't have to worry about it before because my diene was just butadiene. It's symmetric. Doesn't matter which way I flip it, I get the same product. Yeah. But now with 2 things that are not symmetric, I have to consider the charge distribution by drawing their resonance contributors. Okay, let's see what that looks like. With the methoxy group, if I draw the resonance contributors, and now you see the significance why we did this earlier in chapter 8, I've got a resonance contributor with a negative charge on the bottom, positive charge on the top. Same thing for my dienephile. I can draw a resonance contributor with a positive charge on the bottom, negative charge on oxygen. So in that case, I want my partial positives to align with my partial negatives in order to form the major product. Okay. So this will be the product that predominates, right, jumping back a slide, this product is going to predominate over the other one, because that is where I align my delta negative near my delta positive near my delta negative. Okay. So that's a situation where we need to consider the less stable resonance contributors, right? Do they predominate for the resonance hybrid? No, but we need to think about them, sometimes necessary, to figure out how reactants will align themselves to make a product. Okay, so make sure you think about that. If you run into a situation where they're not symmetric, draw the resonance contributors, align the opposite charges, right? Think about that electrostatic interaction. What about other dienes? Okay. Well, keep in mind for this paracyclic reaction to occur, the diene must be in a cis conformation. Okay. And that's a weird notation, s-Cis and s-Trans. What does that mean? Because previously we've just thought about cis and trans being about a ring or about a double bond. Okay. And if you see this notation, s-Trans or s-Cis, it stands for single, right? The S stands for single, so single trans, single cis. And what that does is looks at the position of the double bonds relative to one another across a single bond. So that S is referring to this single bond here in the middle. This is s-Cis because the double bonds are on the same side. This is s-Trans because the double bonds are on the opposite side. Okay. And in order for a Diels-Alder reaction to occur, it has to be in the s-Cis conformation, which you'll notice with the equilibrium arrow is less favorable. Right? Putting the electron density in those pi bonds closer together causes steric strain. So typically, you're going to find dienes in the s-Trans conformation. Okay. But usually, it's a pretty low energy barrier to overcome and allow the Diels-Alder reaction to occur. You just heat it a little bit. That can provide energy to convert your s-Trans to your s-Cis, and then the reaction can occur. But what's an even better way? Oh, I'm getting a little bit ahead of myself. Okay, let's jump ahead a slide just to keep that notation right. An even better way to run Diels-Alder is get something that's locked into the s-Cis conformation, cyclopentadiene. Going back a slide, this diene cannot do a Diels-Alder reaction because it's locked in the s-Trans conformation. Right? There's no way for this to form s-Cis because of the rings. So even if I take this diene and put it together with a Dienophile, no reaction happens. But you see Diels-Alder reactions run with cyclopentadiene all the time because it's locked in the s-Cis conformation. So it's super easy to run. Take that diene, put it together with a Dienophile, it does a Diels-Alder reaction, and it forms what's known as a bridged bicyclic compound, okay, which are popular. You'll see them here in Chapter 8 from the Diels-Alder reaction. You'll see them next semester in Organic 2 as well. Okay? Products with two rings, right, that share carbon, bridged bicyclic compound. And you see here major product because of the stability of having the group away from one another. Right, the rest of your ring from cyclopentadiene, your your ester down here, right? Two large groups, you want them to be on opposite sides from one another. Even though this is in what we would think about being like an axial position, we want them to be apart from one another. Okay? So that's why you've got that major product here. Okay. So bridged bicyclic compounds, right? Two rings that share two non-adjacent carbons as a bridged compound, different from a fused ring, which we've seen a couple of times, right? A bridged compound. Right, so endo and exo products, right? Kind of what we were just referring to, right? Endo and exo, about the pi electrons as well. Stability in the product in terms of thermodynamics, right? But thinking about your transition state, and specifically where the pi electrons are, endo and exo transition states. I thought there was a better picture here. There's not, I apologize. Right, pi electrons, keep them under the ring, okay, because of partial charges. That helps stabilize your transition state. Okay? So two reasons why you're going to favor the endo product. Keeping in mind stereochemistry, and not as primarily concerned with the Diels-Alder, my biggest focus for the next test will be that you can predict the product of a Diels-Alder reaction, right? Specifically the constitutional isomers. But keep in mind, if it forms a new asymmetric center, right, then you're going to form a racemic mixture. If you went from 0 to 1 asymmetric centers, you get a racemic mixture. What if you cause two new asymmetric centers? Well, cis forms cis, and trans forms trans, right? The orientation of the substituents on your Dienophile is what you're looking at. If they were cis to begin with, they have to be cis in the final product. Okay? If they were trans to begin with, they have to be trans in the final product. Okay? So two new asymmetric centers, cis forms cis, trans forms trans. It's pretty easy, right? So it all comes down to, right, your focus moving forward, determining the products of a Diels-Alder reaction. Right? You can also work backwards, determine the reactants, right? Do a retrosynthesis. I pointed this out before. If you see a 6-membered ring with one pi bond, Well, you know how to break it up. Okay? This textbook slide kind of walks you through deleting and adding pi bonds. And if that works for you, great. Right? I kind of think about it as just drawing a line down here, knowing that what's left over here had to be the dienephile, and this had to be the diene. Okay? Whichever method works for you. Oh, sorry, I jumped ahead a slide. Adding pi bonds, deleting pi bonds, that's fine, but just start to get used to the retrosynthesis. Okay. Moving backwards could be, especially at this stage in the game, right? This will be the only time we see bridged bicyclic compounds. So if you see one of those, you know it came from a Diels-Alder reaction. Be able to predict the reactants, or if you see them, right, know how to put them together and perform the Diels-Alder reaction. So the key takeaways: know what it is. I know the terms cycloaddition, paracyclic, dienephile, diene. Know the mechanism. Be able to draw how those electrons are shifting around, and be able to predict the products. Know endo, exo. Know if they're not symmetrical, how to orient them with those partial charges. And as we move forward, get used to the idea of the retrosynthesis.